In order to understand how a CT scan works, it's first useful to understand one of the limitations of the X-ray. So here's my hand being X-rayed, and different parts of my hand, be they blood, muscle, bone, stop varying amounts of the X-ray getting onto the photographic plate. And so we can get an idea of what's going on inside my hand. Now this works pretty well for thin objects like my hand, but it doesn't work as well for things that have got more bulk. Things like stomachs, chests, and skulls. And the reason for that is that when you're looking at an X-ray of, say, a stomach, you can't be sure if you're just seeing one object indicated on the X-ray, or in fact it's a whole series of objects sort of going through the stomach that are lining up to block the X-ray. So CT scans are fantastic because they allow doctors to see inside the body without cutting. So here's a CT scan of a brain, and this is actually what a doctor would see if he cut across someone's skull and looked to see what's inside. But the benefit of the CT scan is that we don't have to kill the patient in the process, so that's a good thing. So here is a typical CT scan setup. You lie down on the aluminium or the silver tray there, and you get pushed through the hoop, and whatever body parts are where the hoop is, then a CT scan is created as though the doctor was slicing down where that hoop is. So now let's look at some of the challenges that are involved in trying to find out what's going inside a body without in fact cutting the body. So a patient lies on the tray and is put through the CT scan. This is a cross section where the hoop is. So we have an X-ray emitter, emits an X-ray, goes through a body part, stomach or chest, which I've represented as a square made up of 9 little squares labelled A through to I. Now as a result of that X-ray hitting the body, some of the X-ray gets through the body and hits the sensor where it can be measured. Now I know this is a very simplified example. We're going to make a 3x3 scan, which I know is not that useful, but this will give us an idea of where to go to, and I'll talk more about the challenges of producing real-life CT scans later. So just so that we get our thinking right, here's an example of one X-ray going through the top part of the body. So 1 billion units of X-ray go into the body and 1,000 units come out. One way we could get 1,000 units coming out is as follows. The first square, we have hard bone, and it only allows 1,000th of the X-ray through. So after going through the first square, we're down to 1 billion times 1,000th equals 1 million units of X-ray. The next square is fluid, and that allows 1/10 of the X-ray through. So now we're down to 100,000 units. And finally there's some muscle, which allows 100th of the X-ray through, which gives us 1,000 coming out. Now this is totally hypothetical. There's obviously lots and lots of different combinations of those 3 squares that will lead to 1,000 units of X-ray coming out. But if you think it through, you'll see that if we multiply A, B and C together, then it must equal the amount that comes out, 1,000 divided by the amount that went in, 1 billion. Now, when we were at school, logarithms were something that a lot of people thought were just there to make life difficult for them. But here's an example where logarithms help a lot. By taking logarithms on both sides, we can change what is a multiplication problem into an addition problem. And we also learned in high school and primary school even that addition is easier than multiplication. It also has the other benefit in this case that it turns that very small number of 1,000 on 1 billion into something more manageable. So because we've taken logarithms, the problem now is to find what A through to I is, but now we've got small a and small I. But safe in the knowledge that just because we've just taken logs, if we can work out the small letters, we can work out the big letters, and once we've worked out the big letters, we can draw the CT scan. Now, the fundamental problem, of course, is that there's still an infinite number, essentially, of solutions to this problem. We could have 1 + 1 + 4 = 6, or 2 + 2 + 2 = 6. And the way that we solve to find out what A to I is that we need more X-rays. So now let's imagine that we shine in 3 X-rays horizontally and 3 vertically. So you can see the second horizontal gives us an equation with D, E and F. And this has now become essentially a purely a mathematical type of problem, a bit like a Sudoku. We know that the total across the first horizontal is 6, then as we go down 15, and then let's just imagine it's 24, and the vertical totals are 12, 15 and 18, and our task is to fill this with numbers from 1 to 9, but unlike a Sudoku we can have repeats, because if you remember when we were talking about that first row that adds to 6, we definitely can have 2 plus 2 plus 2, so we can have repeats. So you might like to stop the video and have a think whether you can solve this number problem. So actually the last time I did this talk to a live audience made up almost all of adults. The only person who seemed to be able to solve it quickly was a 9 or 10-year-old child who yelled out 1, 2, 3, 4, 5, 6, 7, 8, 9, and sure enough that is a solution. So once we have that, we can then use that to create the CT scan. So we're just about to rush up the corridor to show the doctor the CT scan of the patient when we hit another problem. So you might like to have a quick think, what's the problem now? Well, here's a problem. You can actually have more than one solution here. Here's another set of 9 numbers that satisfy all the totals. And in fact, it turns out that there's 6 others. So how are we going to solve that problem? Because of course we need to get to a unique CT scan, because the doctor doesn't want us turning up with 6 CT scans and saying, well, it's one of these, but I'm not sure which one. So if we go back to where we had the X-rays going horizontally and vertically, the way to solve this problem is to start using the diagonals. And you can see there's lots of diagonals. I think there's about 10 diagonals. So by taking enough diagonals, we can get to a unique solution. Okay, so that's good. So now we rush up the corridor with our CT scan. It turns out that it was in fact that second one, 114, 555, etc. So we take that scan up to the doctor, and he says the obvious thing that we discussed before, this is useless because it's only made up of 9 squares. It's a 3 by 3. I need like the initial CT scans, which are about 80 by 80, or more likely the modern day scans, which are 1000 by 1000. So we go back down to the corridor and we think how we're going to solve this. So we now divide the body up into, say, 100 squares by 100 squares, and we start shining through the X-rays. And now we come to a problem. That is, the computer is sitting there with all the X-ray information, trying to solve for this unique CT scan, which is now 100 by 100, and it's taking a lot of time. So it ends up taking 2 weeks. So now we go down to the corridor and show the doctor. He says, wow, this is a fabulous scan. I can see everything. Unfortunately, the patient died a week ago. So the problem with this style of CT scan, which I think of as the algebraic method of doing CT scans, which was the original method, is that it's too slow, particularly as doctors are becoming more and more demanding about CT scans. They no longer want 1 scan, they want 30 or 40 scans. And in fact, it's getting even worse than that now, or better, arguably, medically, as there's talk of things like virtual reality type of CT scans where doctors can walk through. So the algebraic method is simply too slow for the modern day uses of CT scans. So we can now talk about the current method for CT scans, which I think of as the calculus method. So let's have a chat about that. Actually, before I do that, let me point out that I have a YouTube channel which has got other videos on how things like JPEG, GPS, Google search and encryption works, and then there's lots of other mathematical videos for early university students, those who are interested in interesting and important theorems in mathematics, and quite a bit of fun maths as well. You can also see my website there. Drop me an email if you want to discuss me doing a talk, either live or Skype, for your university or school or corporation. Okay, so now let's talk about the calculus method And to do that, let's go back to 1917. And an Austrian mathematician writes a paper. It's a pure mathematics paper. It's got nothing really to do with CT scans or X-rays. And Radon asked this question. He said, imagine we've got a body of some sort, which has got a boundary around it. Here you can see it, the boundary. And within the boundary, every point has a value. So this red dot indicates a point that has a value. And what we're trying to do is find out the value at this red point. He said, imagine you draw a horizontal line through the red dot. Now, if you plotted all the points along that line within the boundary, you would end up with a graph, and a graph of a function essentially. And you could work out the area under that curve, or the integral. And imagine you were given that information. Now, if you're not familiar with integrals, you could consider that you're given the total of all the values as you go along the line within the boundary. So Radon said, well, if that's all you're told, you can't work out the value at the red dot. But then he said, imagine that we start rotating the line, but always going through the red dot. And we've actually got access to the integral, or the total, for every single line that goes through the red dot. Now, he said, you can actually work out the value of the red dot amazingly, using some quite complicated mathematics involving something that's now called the Radon transform. This is perfectly suited to the CT scan problem. Each of those lines can represent an X-ray going through the body, passing through this one point, the red point, and so using Radon's genius, we can work out the value of the function, or the value of the CT scan at that point. And if we can do it for that point, we can do it for every point within the boundary. So that's how the modern day CT scan works. So I hope that's given you a bit of an overview about CT scans and how they work.